Okay, in this section 3-3 we are talking about complex roots of polynomials. And so up to this point, what we have discussed is that an nth degree polynomial can have at most n real zeros. So think about a quadratic, a second degree polynomial that has a parabola, a U-shaped curve. And so what we've said is if that quadratic crosses the x-axis at 2 points, it's got 2 zeros. And we said if it hits at 1 point, just at the vertex, it's got 1. And we said that if it's translated up and does not hit the x-axis, then it doesn't have any zeros. Well, what we really should have been saying is that it either has 2, 1, or no real zeros. In the complex number system, then we can improve that statement to say that in the complex number system, every nth degree polynomial function has precisely n zeros. All right? And so for the example of the quadratic, when it was translated up and didn't hit the x-axis at all, okay, we said that it had no zeros, but it had no real zeros. It actually had 2 complex zeros because now, whatever the degree is, okay, it has exactly that many zeros. Okay, some of them may be strictly real, and some of them may have an imaginary component, making them complex. Remember, real numbers are also complex numbers. Real numbers are a subset of the complex number system. All right, so keep that in mind. And so now let's take a look at what is known as the fundamental theorem of algebra. Here's what it says. It says, if f of x is a polynomial of degree n, where n is greater than 0, then f has at least 1 0 in the complex number system, right? And so what you might be thinking is, well, coach, it says that it has at least 1 0. So how does this theorem show us that it has exactly n number of zeros? Okay, so here's how it works. Think about it like this. Let's say that you have a polynomial of degree 5, right? Well, the fundamental theorem of algebra says that it has at least 1 0 in the complex number system. So let's say we find that 1 0, all right? Well, turn it into a factor and divide it into that degree 5 polynomial, then you're down to degree 4, right? Well, apply the theorem again to the degree 4 polynomial. It has at least 1 0. All right, find that 0, turn it into a factor, divide it by the degree 4. Now you're down to degree 3. So at this point you would have a degree 3 polynomial. You've already found 2 zeros, right? Because if it's a factor of the degree 4, then it also would be a factor of the original degree 5 polynomial. All right, so you take that degree 3, apply the theorem again. It has 1 0. Find it, turn it into a factor, divide it out. Now you're down to degree 2. Okay, it has 1 0. Find it, turn it into a factor, divide it out. Now you're down to degree 1. Find it, 0. And then you've got all 5 zeros of the original degree 5 polynomial, right? And so that's how the fundamental theorem of algebra actually can show us that whatever the degree is, it's got precisely that degree number of zeros. And then also along with that, we have the linear factorization theorem that says if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors, because for each one of the zeros, right, each one of the zeros, you can turn those into a linear factor. So if it's got n zeros, then it also has n linear factors likewise. All right, let's work some problems out now. Let's say we wanted to find the zeros of this function. And so how would it work? Okay, so first thing that we would do is go through and factor this thing out by hand. And so we can factor that into a product of 2 binomials. And so we know x squared goes here and here, x squared, x squared. All right, so to get -1, I'm going to have to put -1 and +1. All right, -1, +1. All right, so let's just double check all of my terms. X times x is x squared, right? -1 times +1 is -1. And there should be no middle term. So -x squared plus x squared zeroes out, and there is no middle term. So we know we factored it correctly. And so now I'm going to take that thing and I'm going to factor out the first set of parentheses. And so we'll have x, To get a negative, we know we have to go plus 1 and minus 1. And once again, 1 times negative 1, negative 1. And the middle term zeroes out, so we're good. Now let's go and factor the second set of parentheses. All right, so we do know, again, we need x and we need x. Now, let's try to factor that in terms of like the real numbers. So if I wanted to get a positive one, I could go positive times a positive or a negative times a negative, and to get 1, I got to go 1 times 1. So let's say we go plus 1 plus 1. Well, we're good on the end. However, look at the middle term. It's supposed to zero out, but x plus x is 2x. So that's not the right factorization. If I change it to minus and minus, negative times a negative makes a positive. 1 times 1 is 1. We're good on the end, but we're still not good in the middle. Negative x minus x is negative 2x, and it doesn't work out. So at first glance, you're going to be saying, well, this doesn't factor. Well, it doesn't factor in the real number system, but if we throw imaginary numbers in there, we can get it to factor. And here's how. All right, so let's think about it like this. Okay, first of all, if I want the middle term to zero out, it's got to be plus and minus. Okay, it's got to be plus and minus, because that's the only way that I can get the middle term to zero out, right? Otherwise, it won't zero out if it's not a plus and a minus. Okay, so I know that's got to be there. Here's the next thing. The next thing is, not only do they have to be plus and minus to zero out, they've got to be the same number here to zero out. Okay, so I already know that I'm going to have to put an imaginary number here, but I've got to put the same one here, right? So like if I put 3i here, I got to put 3i here to make it zero out. 2i here, and so on and so forth. So what I've got to try to figure out is what's the same imaginary number that I can put here and here that whose product is a positive 1. Well, if I put I here and I here, let's see what happens. First of all, positive times a negative is a negative. And what's I times I? Well, I times I is I squared, and we've already learned that I squared is what? Negative 1. All right, so negative and a negative make a positive, so positive 1 is the correct factorization here. And then, of course, the middle term zeroes out. Okay, xi minus xi is 0 in the middle, and we factored it. So what is not factorable in the real number system is factorable in the complex number system. All right? And so now that we factored this thing down completely, we can actually write out the zeros and get our answer. So what are our zeros? Well, it's plus and minus 1. And it's also plus and minus I. And so let's see that it fits the fundamental theorem. This was a degree 4. We've got 4 zeros. 1, negative 1, I, and negative I. And then those are your 4 answers. Okay? Let's try another one. Let's say I wanted to find the roots of this particular function. So once again, we will start factoring. First thing that we can do here is pull an x out. X squared plus 4 is what we will have now. And so I'll go f of x equals x. Now I can work on factoring that set of parentheses. So that'll be x and x. And so now, once again, there's no real numbers I can put here that would actually make this factor out correctly and zero out in the middle. However, if I want it to zero out, I know I got to be plus and minus. But now I know that I need an imaginary number here, and it's got to be the same imaginary number in order to zero out in the middle. And so what times what, imaginary number-wise, would multiply together to give me a positive 4? Well, it's going to be 2i and 2i. Because think about it like this. Positive times a negative is a negative. 2 times 2 makes 4. I times I is I squared, which we already know is negative 1. And then, of course, that multiplies together to give me positive 4. All right, so once you understand, when you're trying to factor these out, once you understand that it's got to be a plus and a minus, and the same thing has to go here, it makes it kind of easy to factor it out in the imaginary number system. Okay, and so from here, we're pretty well done factoring it. So now all we got to do is just write out the zeros, which would be 0, and it would also be plus or minus 2i. All right. So there you go. Alright, now let's talk about example 3. Okay, so on this one we want to list out all the zeros of this function. Now, here's the first thing that we would have to do. We would have to graph to get real factors. Okay, got a graph to get the real factors, and here's kind of how that would look. Okay, if we go now to our let's see, go to our Desmos calculator here, and I can go ahead and put this in here. So let's just type it in. It's going to be y equals x raised up to the 5th plus x raised up to the 3rd plus 2x squared and minus 12x plus 8. Alright, so there's my graph, and I can see that I got 2 real factors here, and those zeros are at -2 and 1. So if I wanted to write those as factors, I'd write it like this. I'd write it as x minus 1, that's one factor, and x plus 2. Alright, so that's another factor. So those are my 2 factors based on graphing it and looking at the real zeros. Alright, now, here's the next thing that we would have to do. Okay, we would have to use synthetic division 5 times on this one. We'd have to use synthetic division 5 times would be our next step. Because remember, we're trying to factor this completely down so we can get all of the zeros. Well, graphing gave me 2 of the factors, and so now what I would have to do with these factors is divide it into this polynomial. Okay, and so we would have to divide x minus 1 into this. We would see that it would go even, so I know that's one of my factors. Of course, we already knew that. Okay, but here's the deal. When I divide this and it goes even, I would have to divide it into the result, into the quotient again, because I don't know the multiplicity of this factor, right? Because remember, sometimes we learned in the last unit that these factors could have multiplicity higher than 1. Well, then that counts as more than 1 zero. You see what I mean? So when I divide this out, it would go evenly, which means I would have to divide it into the quotient again, and once it divides and it doesn't divide evenly anymore, that's how you know the multiplicity stops. So x minus 1 would actually divide into that quotient again, but it would not divide a 3rd time, so that would tell me that x minus 1, that factor, or that 0 would have a multiplicity of 2 because it divides evenly as a factor twice. Alright, so x minus 1 has a multiplicity of 2, and then once I divided it into that 3rd quotient the 3rd time to see that it doesn't divide evenly, then I can stop there and say, oh, it doesn't divide a 3rd time, so now that I know that the multiplicity of that factor is 2. So once I've exhausted the multiplicity of this factor, I can go back to that 2nd quotient and then divide x plus 2 into that. I would see that that one goes evenly to the quotient that's left, right? Then I would have to divide it into that result again, right, to show that it doesn't go evenly anymore, which means the multiplicity of x plus 2 as a factor is just 1, right? So the multiplicity of -2 is just 1. So 1 factor is all that we need from that. Now, what's left over once I divide these out of there would be x squared plus 4. All right, x squared plus 4. And so to finish it out, I know that I've got these factors. And now I'm going to try to factor that last set of parentheses. into a product of two binomials. I know I need x, I know I need x. I know I need plus and minus. That's the only way the middle term will zero out and disappear. And so to finish factoring this out, I know I need the same number here and here as far as the imaginary number is concerned. So that'd be 2i and 2i. Okay, so once again, positive times a negative is a negative. And so 2 times 2 is 4. I times I is I squared, which is negative 1. And it gives me positive 4. That's the same one that we had actually factored out in the previous problem. All right, and of course the middle term disappears. 2xi minus 2xi is 0. All right, so we factored it correctly here now, and these are all of my factors. Once I've got all of my factors, I can write out all of my zeros. I'm going to write 1 twice because it has a multiplicity of 2. I'm going to write negative 2 once, and then I'm going to write out plus and minus 2i. Okay? And then so those are all of my factors. Notice there's 5 of them. We know that's correct because this was a degree 5 polynomial. So it must have 5 roots. All right? Okay, now let's talk about this for just a minute. I know that right here I said use synthetic division 5 times and I didn't actually do it. Okay? Now, listen. I am going to show you something that's going to make your life a lot easier. Okay, so on the internet you can find a polynomial roots calculator, right? And so I'm going to go ahead and show you this, and here's the reason why. Because I know that you know how to use synthetic division. Okay, we've already had a section over synthetic division, and I know that you are proficient at doing that. Okay, so I don't feel like it would be very efficient for us to take this problem, okay, and turn it into 2 pages long by adding 5 synthetic divisions to this problem. All right, so I'm going to show you how to use the polynomial roots calculator online, and I'm going to show you where to get it, and you can use it. Okay, so if you just go up here and you Google polynomial roots calculator, there's several to choose from. The one I like is Math Portal, so you can go to that one. And so you just come in and you type in whatever polynomial you want the roots of. So we want x to the 5th plus x to the 3rd plus 2x squared minus 12x plus 8. Find the roots. And notice it gives us the same thing that we got when we factored it out on paper. So we got 1 with a multiplicity of 2. We got negative 2. And then we've got 2i and negative 2i. All right, so feel free to use this polynomial roots calculator that you can find online, because that'll save you some time. And like I say, I already know that you know how to do synthetic division, so I don't see any need for us to add 5 synthetic divisions to this problem. All right, it's not efficient. I'm not testing in this section if you know how to do synthetic division. We've already had a section on that, and so you can feel free to use this on your quiz, and when we take the test over this unit, you can feel free to pull this tool up online and help you to work the problems that way as well. I don't mind that at all. The reason why I don't mind that is because if we were sitting in the classroom, I would put a TI Inspire calculator in front of you, which also has a polynomial roots calculator. To get there, all you would have to do is press Menu, Algebra, Polynomial Tools, Complex Roots, and then just type this in here, right? And of course, it works kind of like the InSolver, the equation solver. You have to put comma x after it to tell what variable you're trying to find the roots of. and then you press enter, and then it gives us the same thing that we got by hand and on the other calculator, the online calculator. So 1 has a multiplicity of 2, we got -2, and then we have 2i and -2i. And so, like I say, feel free to use the one online for any of the problems that we do. Feel free to use it on tests, that's fine, because if we were sitting in the classroom and I were to give you a test, then I would hand you a Inspire calculator to use on the test. So like I say, you don't have to feel like you're cheating or anything like that when you pull the one up online. It's fine, because I would give you this calculator if we were sitting in class anyway. So you would have this at your disposal, and I would encourage you to use it. And so, like I say, in this section, we're not testing whether you know how to do synthetic division. I know you know how to do synthetic division, and so that's why I'm not making you divide it out with synthetic division 5 times. All right? But if you didn't have a tool like this at your disposal, you would know how to do it completely by hand. And that's the important thing. So, remember, a calculator is not a substitute for knowing how to do the procedure. It is a tool to allow you to do the procedure more quickly once you know how to do it. So, when you were younger, your teacher didn't give you a calculator before you learned how to multiply. So you learn how to multiply big numbers first, and then the calculator is a tool to help you do it more efficiently after you know how to do it. And so it's kind of the same thing with this. All right, we know how to do it by hand if we had to, but if we have a calculator to make our work more efficient, then we can feel free to use it. All right, so I'll be back with the next lesson shortly.